Okay, so we're going to wrap up our log unit by learning how to solve more complicated log functions using some of the properties that we've learned so far, and keeping in mind some of the exponential solving that we've done. So two key things to keep in mind when we're solving exponential and log functions are the one-to-one property, and for logarithms that looks like this. If we have log base b of x equal to log base b of y, then we can say that x equals y. Now keep in mind this is only true when there's a single log on either side of an equal sign, not a plus or a minus, but it has to be on opposite sides of an equal sign. And the same is true for exponentials, right? If I had b to the x equals b to the y, then we can just say that x equals y. And that's how we solved all our exponential functions in the past, where we just made sure we had a common base. So keep those in mind as we're solving today. And then don't forget your inverse property. This is going to help when we have some sort of exponential expression or a log expression, and we're trying to solve. So this property says log base b of b to the power of x equals x. Right? So essentially a log of base b and an exponent with base b, they're inverses of each other. They undo one another. Okay, so I think we can handle these pretty easily. This isn't a bad place to pause the video and see if you can do these first three and then check your answers. Okay, so let's start with this exponential expression, 2 to the x equals 32. So the first thing you want to do is see if maybe we can find a common base. And 2 to the x, and then 32 is a base 2 number, so that's 2 to the 5th. Therefore, x equals 5. Pretty straightforward. If we look at number 2 and we're looking for, well, what's our common base on either side? We've got 1/3 and 9. So you do want to identify that that's base 3. We can put both sides in the same base, so we're going to do that. 1/3 becomes 3 to the negative 1. That's how we get our fraction. And then 9 is 3 squared, and then bring down that power of x. I put parentheses around it to remind you that when we have a power raised to a power, we multiply those powers. So now I can basically cancel out these bases using that one-to-one property, and I get negative 1 equals 2x, and then we'll just solve all the way. X equals negative 1/2. To solve number 3, we don't have to do anything with our base because those are already common bases, so they just essentially cancel. And we get 2x equals x minus 8. And then let's just do our algebra style solving. So we get x equals negative 8. Now if you ever wanted to check your work just to see if it makes sense, we can do that. You can plug your answer back in. That's something that we definitely need to do on these log equations that we've got here. So we're going to start with number 4. And there's a couple different ways to tackle it. This would probably be a good time for you to pause and try this one on your own and then come back and see how we do it. But like I said, there's more than one way to do it. Okay, so we can simply, knowing that we're going to go towards a one-to-one property, I can just add this natural log of 3 to the other side. And then I'd have natural log of x equals natural log of 3. And then with that one-to-one property, those cancel, and I just get x equals 3. You just need to check and make sure that if you plug that answer back in to our original equation, just make sure we're not taking the logarithm of a non-positive number, because we can't do that. The other option on this one was to condense these down to one log, but if you just have one on either side of a subtraction sign, this isn't too bad. But let me show you what we would do if we were going to condense those down. We would have brought these two together using our quotient property. So this is subtraction, so I would have rewritten this as natural log of x over 3 equals 0. And then we'd rewrite it in exponential form. So in exponential form, this is base e. So we'd say e to the 0 equals x over 3. 1 equals x over 3. Therefore, x equals 3. So I think you can see that on this case, this is the longer way around. Probably not the most efficient, but there's not always just one way to get there, so just keep that in mind. All right, let's try number 5. For number 5, we have a log on one side and a number on the other. And in this case, what we typically want to do is we want to rewrite it in exponential form. So I'm going to go ahead and do that right now. All right, so when we rewrite this in exponential form, don't forget natural log has base of e. Now, I'm just writing that there as a reference, so we know when we go to roll it into exponential, we know that it's going to be e to the negative third equals x. Now, if you wanted to find that decimal, you could type it into your calculator. This is sufficient, though. If you're wondering what that is, it's about 0.0498. But e to the negative 3 is a lot more precise than that. On number 6, same deal, except this time we're dealing with the common log, which has a base of 10. So we're just going to roll it into exponential. We got a log on one side and a number on the other. So in that case, we roll into exponential. 10 to the negative 1 equals x. We can simplify 10 to the negative 1. That would be 1 over 10. And that's our answer. Now just make sure that's a number we can take a log of. It's small, but it's not negative, so that's fine. So something to keep in mind here that you're going to want to do on problems like this. For both of these, we wanted to rewrite in exponential. And that's when we had a log on one side and a number on the other. Okay, so now let's move on to something a bit more challenging. And the reason these are a little more challenging, in particular, starting with this first one, or some of these, is that we have to isolate, we have to do some algebra before we can write the equation in another form, or before we can use logarithms or exponents to solve. So these are all exponents right now. And if you look at number 7, e to the x equals 7, between e and 7, we do not have a common base. So since we don't have a common base, we need to rewrite as a log. Okay, so let's go ahead and do that. Okay, so when we go ahead and write it as a logarithm, we're going to use the base of the logarithm, use the base of this exponential right here. So a base e logarithm is the natural log, and the natural log of 7 equals this exponent. And so remember what we've talked about in the past is that natural log of 7, we're using this log so that we can break apart e, the exponent's base, and its power. That's how we separate the e and the x. So our answer should always be whatever the exponent is. Now, natural log of 7, if you type that into your calculator, we're going to go ahead and get about 1.946. So if you're asked to round, in this case we were rounding to the nearest thousandth, then we would write 1.946. Other times you might just leave it as the natural log of 7. We don't have to have a calculator to write that. Okay, so let's take a look at this next one here. We've got 3 times 2 to the x equals 42. Now, a common mistake that happens here is people try to distribute that 3 in because it's sort of a habit of most of ours. But the power is what has to happen first. And whenever we're solving this, we just need to isolate the base and the exponent. So to get rid of that 3, we're not going to distribute it in. We're actually going to divide, because I need 2 to the x isolated. So these 3's cancel, and I get 2 to the x equals 42 divided by 3 is 14. Now here we go again. We have 2 and 14. Those do not share a common base, so we can't just do 2 to a power and have a whole number. We're going to have to use a logarithm. So let's rewrite it in its log form. So we're doing the same thing on this one. And then whatever the base of the exponent is goes here. The 14 becomes the argument of the logarithm, whatever we're taking the log of. And then our x is our exponent, and that's what we're trying to solve for. All right, so we've got log base 2 of 14 is x. And so this is when we need our calculator and our change of base formula to help us out. So if you remember that from last time, it says we can rewrite any logarithm as the log of the argument divided by the log of the base. So in this case, the argument, what we're taking the logarithm of, is 14, and the base is 2. So if you type this into your calculator, and please remember to put parentheses around that 14 before you do the divide sign, and then divide it by log 2, we're going to get 3.807. Okay, this is a great place to pause and try number 9, and then come back and check and see if you got it right. Okay, so let's take a look here. Let's just identify what it is we're trying to isolate, right? Like over here we wanted to isolate the 2 to the x. On problem number 9, we want to isolate the e to the x. So that's what we're going to do, and we'll just start by subtracting 5. So e to the power of x, e to some power equals 55. We're just going to figure out what that power is. Again, we don't have a common base between e and 55, so we're going to rewrite it as a logarithm. So base e means we're going to go ahead and write natural log of 55 equals x. And then it's calculator time. So go check in your calculator, type in natural log of 55, and let's make sure we round it 3 decimal places. And once you do that, you should get 4.007. Okay, pause here and then come back and check your work on these. They're mostly straightforward. Let's have you do 10 and 11 and then come back and check. Okay, so if we're looking at number 10, again, let's just identify what we're trying to isolate. In this case, it's just e to the x. So we've got several steps that we need to take to make that happen. So I'm going to subtract 5, and then I get negative 3 e to the x equals negative 3. I'm going to divide by negative 3, and then we'll get e to the x equals 1. Now, we can rewrite this as a logarithm, or you might already know what the answer is. If we raise a base to a power and get 1, we know the answer has to be 0. But just to make sure we understand, I'm going to rewrite this. Natural log of 1 equals x. That means x is 0. All right, so don't even need a calculator for that one if you understand your properties about logarithms, that taking the log of the number 1 is always 0. Okay, so let's check the next one real quick. Again, identify what we're trying to isolate. In this case, we're going to isolate this 10 to the x minus 6. And then we'll go ahead and solve from there. So the first thing I'm going to do is don't distribute that 5, divide by it. So 10 to the x minus 6 equals 7 over 5. I'm just going to rewrite that real quick as 1.4. And then 10 and 1.4 don't have a common base. So we'll rewrite this as a logarithm. 10 to the x minus 6 equals 1.4. As a logarithm, we'll use this for our base, 10, which means common log. And you don't have to write the base 10. So log of 1.4 equals x minus 6. And so we're going to get a decimal here that we're going to end up having to add 6 to. So once you type that in your calculator, you'll do the common log of 1.4 and then add 6. And then we should get x equals 6.146. Okay, that's our quick little refresher. We'll continue in the next video starting at number 12.